Yeah, so as Daniela said, I'm Alex, I'm the president of Space Exe, and I'm going to be talking about my master's project. So my project is working with Professor Nathan Main to take something called the Unified Model, which is the climate and weather forecasting model used by the Met Office for weather forecasting on Earth, but applying it to Mars. So first off, does anyone know what this film is taken from? Yeah, The Martian. So for those who don't know, The Martian is a 2015, I think, science fiction film. Basically, Matt Damon plays an astronaut who gets abandoned on Mars due to a massive dust storm. So as the opening of that film suggests, dust storms on Mars can be pretty dangerous. And as companies like SpaceX or government agencies like NASA spend billions of dollars on manned exploration on Mars, some form of weather forecasting would be quite useful. So, as I think we all know in Britain, the weather forecast is good and sometimes it doesn't work. So why are we interested in another planet? Well, like I said, we're interested in the prospect of manned exploration, but we can also, from the surface, see these tracks on the surface. And what these suggest is, very long ago in Mars' geological history, there would have been water on the surface. So we're interested in then the potential of prehistoric life, so we need to understand what the climate is doing to understand whether life could actually exist. So a good place to start, I suppose, is clearly state the difference between weather and climate, because if you spend any time online, these two words get intermixed constantly and the understanding is quite poor. So weather is basically the short-term changes in the atmosphere. So for example, 9 degrees highs of an extra today and light rain, the chance of light rain. But with climate, we're looking more long-term. So extra has quite a mild climate, wherein the summer can be changeable between sunny spells and rainy spells. But we're looking over the course of thousands or even millions of years. So now, you may be wondering, well, Mars is a faraway planet. On Earth, if you're interested in the weather, we can just walk outside and take some data. How does that work on Mars? Well, currently on Mars, we have 3 active rovers. So we have the Opportunity rover here, and there's been 3 rovers in the past, and these rovers collect data. There's the other orbiters, as it's just orbiting the planet, and lander missions, which are basically helicopters which are deployed to measure sort of a vertical structure of the atmosphere. So to give you a comparison, the UK currently has over 200 weather stations. So you've got 200 data points in the UK, versus 40 across the entire planet. So the amount of data you collect is very much different. So what is the unified model? So the UM is as I said, the unified model. So it can do 2 things. It can do long-term climate forecasting, but also short-term weather forecasts. And it's the global climate model currently used by the Met Office. So how does something like that work? Well, first off, you have your planet, and you split up into a massive grid, so you can say lines of longitude and latitude, and also then the vertical structure. So in each one of these grid cells, we're interested in a couple of things. What's the temperature? What's the air pressure? How is material then flowing? So we do radiative transfer calculations like this, which basically shows you if you have solar wave radiation coming in from the sun, where is everything going then from that? So then you can say, okay, in each cell, there's this amount of incoming radiation, this amount of outgoing radiation. So you'd expect a temperature of, let's say 5 degrees Celsius, for example. And from temperature, you can work out pressure, and from pressure, you can know how the wind is flowing and how then, if there's clouds in the atmosphere, how that's flowing and how heat is also then moving. So what are some of the main sort of things that make up the Martian climate? Well, first you got to consider, how does Mars orbit the sun? Is it a circular orbit or is it more elliptical? What's actually the orography on Mars? So for those you know, orography is the study of the land, or the distribution of mountains and the landscape across a planet. So to give you an example, Exeter is quite hilly, other parts of the, and X is quite hilly, somewhere like, I don't know, Florida is quite flat. You also then consider Mars and dust. Mars is basically a planet where desert and dust is a big part of that. Then you also consider, okay, what's the atmosphere made up of and how does that change throughout the year? So I'll first like to start with talking a bit about the orbit. So the Earth orbits the Sun in a circle in the fact that throughout the year, it's the same distance from the Sun. This does not change. But for Mars, it's slightly more elliptical. So it has an eccentricity of about a tenth. And 1 day on Mars is what we call a sol, and a sol is roughly 24 hours and 40 minutes. And then 1 year on Mars is 670 odd sols. So we start the Martian year by hair in Northern Hemisphere summer. And the planet is 1.6 AU away from the Sun, and 1 AU is the distance from the Sun to the Earth. So it's 1.66 times the distance. So we have summertime in the Northern Hemisphere and winter in the Southern Hemisphere. And throughout the course of a year, it receives about half the amount of sunlight than the Earth receives. So we do... One second. So then we do a quarter of the orbit, and now we have autumn in the Northern Hemisphere, and it's now spring in the Southern Hemisphere. But once we get round to Northern Hemisphere winter, we have summertime down in the south. You're actually closer to the Sun, which means that on average, your temperature during the Southern Hemisphere summer is roughly 10 to 20 Kelvin, which is equivalent to 10 to 20 degrees higher than during summertime in the Northern Hemisphere. And then we swing back round to Northern Hemisphere spring, and then we're back where we started with clearly 1 year, and it's summertime in the Northern Hemisphere. So this is then a sort of satellite image capture of Mars. And what I like about this image, it captures quite well one of the interesting and main features about the Martian surface. You have this really interesting dichotomy between a very flat north and a very sort of mountainous and hilly south. So this topography map captures it a bit better. So in the north, you have what we call the lowlands. So it's very mainly flat, but in the south, you then have things like the Forest Rise, which plays host to Mount Olympus, and then the Hellas Basin, which is like which would have been long ago probably like some sort of ocean, which is now dried up. So these mountains, which are present throughout the south, one of the things they created what we call slope winds. So if you imagine your mountain, one half will be in the sun, but the other half is going to be in the shade. And as you know, if you, I don't know, turn your heating on, but for some reason leave a door open, all that heat's going to escape. So the air will flow from the hot region to the cold region, which will then drag material up the mountain. Now, currently in the unified model, we have a map like this, but what we don't have are maps of albedo and formulinosa. So albedo describes how reflective the surface is. Something like snow is highly reflective, so it's about 0.5. But these rocks are around 0.2, so we're assuming constant values for those. And formulinosa describes how slowly something is to reach a sort of equilibrium, a formal equilibrium with its surroundings. So we have to introduce those values into our model of Mars. Currently, those are just constant values. So to give you an example, this is a scale diagram showing Mount Olympus compared to some of the biggest mountains on Earth. So you have Mount Everest, which is 8,800 meters, but Mount Olympus is 22,000 meters. And as a now comparison, the base of the mountain is roughly the same size as the country of Poland. So it's the biggest mountain in the solar system by far. So the other interesting thing about Mars is the dust. So we have two observations. This was taken in June of 2001, and this was taken in September. During June, you can clearly see the surface, but by the time you reach September, there's been an annual dust season which has obscured all of the surface. You can't make out anything. So we know from observations the dust gets from the ground up into the atmosphere. But how does that happen? Well, there are two methods. You have saltation and you have dust devils, which sounds more interesting than saltation. So saltation is a similar process to what happens in rivers in the fact you have flowing horizontal winds, and these winds will pick up big boulders and as we all know, what comes up must come down. So once those boulders, they come up and they hit the ground, at the impact, they throw up a lot of finer grains of materials. Now, unlike Earth, the Martian dust is about 1.5 millionths of a meter. On Earth, that's about 10. Dust on Earth is about 10 times that size. So to do a mix of that and also lower surface gravity, the suspension, they stay in the air for much longer. And boulders then will be called creep. And the other thing are dust devils, which they're basically tornadoes. So this is an observation from an orbiter. We have the track of kicked up dust, the actual dust devil hair, and then the shadow casted by the dust devil. So a dust devil basically forms because you got the sun heating up a bit of the ground, and because of that, air is going to rise, and under the right conditions, the air will start to circulate. This rising air will start to circulate. But these, through saltation and the horizontal winds, this will drag dust in. So you get then the formation of a dust devil. Now, these form enough, and they're kind of called tornadoes, but then you also get like no ones enough, which, because there's a lot more happening in the atmosphere, they only rise to a couple millimeters, whereas these can be meters taller than Mars. So I was trying to highlight this sort of schematic to show you how important dust is in the atmosphere. So what you're looking at is outputs of the unified model taken during month 9, which corresponds to summertime in the southern hemisphere and the peak of the dust season. So along the horizontal axis, you have then latitude, and going up vertically, you have how high you are above the surface. And this has been averaged across lines of longitude on the planet. And you have the base scenario, so nothing's been changed, and then you have a scenario where you've turned off the radiative properties of the dust. And what this is showing you is dust acts like clouds on Earth. They keep the atmosphere warmer than you expect. And without the dust, temperatures drop by about 20 to 30 Kelvin. So as I can show you, dust has a massive impact on the Martian atmosphere. So that then brings me on to the atmosphere. What's it made of? Well, unlike Earth, Mars is mainly composed of carbon dioxide, about 95%, and then small amounts of nitrogen and argon. Whereas the Earth is about 70% nitrogen and then 21% oxygen. Now, you may be thinking, well, 95% CO2, that's going to lead to really high temperatures if you think of global warming. We are concerned about small changes in the Earth's atmosphere, but at 95% level, that must be boiling. But the difference is the Martian atmosphere is incredibly thin. Pressure at the surface is somewhere around about 50th of the sort of pressure at the Earth's surface, I think. So then that means that the heating caused by the CO2 is only 5 to 6 Kelvin, with similar amounts of CO2 on Earth will lead to heating of 20 to 30 Kelvin. And also, because of this low surface pressure, liquid water cannot exist at the surface. If you say you had an ice cube and then you heat it up so it melts into water, as soon as it becomes water, it becomes a gas due to it being below the triple point. The low surface pressure also prevents a runaway greenhouse effect. To give you an example, Venus also has similar levels of CO2, but has temperatures of up to 400 degrees Celsius because of how thick the atmosphere is. So the other thing we have to consider are the North and South Pole. Now, as you know, the poles on the Earth are covered in snow for the time being. But the problem with Mars, we have then ice caps of carbon dioxide at the North and South Pole. Now, as I mentioned, during Southern Hemisphere summer, we're at closest approach to the sun, meaning that the melting rate of the CO2 at the Southern Hemisphere is greater than the freezing rate of CO2 at the Northern Hemisphere. So what this leads to is a yearly cycle in the surface pressure. So green and red lines, those are surface pressures captured by the Viking 1 and Viking 2 landers on the surface. So you can see it starts at around 800 odd pascals and drops down to 600 and up to about 1,000. Currently, the blue and black lines are the unified models. One of the things we have to introduce to our model is this CO2 cycle, and as you can see, we clearly don't have it. So you just think of how much that pressure is varying for the year and how much CO2 is in the atmosphere. This CO2 cycle is one of the main building blocks you actually need to introduce into our model during this Masters project. So as something is a bit more visual, this is actually an output, a visualization of the unified model. So this kind of shows you what a typical day in the Southern Hemisphere summer is like. So those arrows are the winds about a kilometer above the surface. We've also then scaled up the orography by a factor of 30. And then this sort of thing above the surface is an extract of the dust just to show you what it's like. So currently, within my project, we have many things we need to introduce, but our goal is to then have a fully working climate model of Mars, which can be used for manned explorations. Now, like I mentioned, on Earth, to confirm our models, we can just walk outside, collect some observations. But how does that work on Mars where you can't really take a rocket to Mars and get your data? So what we can do is we can compare to other models. So in this field, one of the best models that exist is something called the Planetary Climate Model. It's created by a university in Paris, which I'm not going to try and pronounce. But on the left, you have the unified model, and in the middle, you have the PCM, both during month 9. Then on the right, you have the difference. And what this plot is trying to show you that for zonal winds, which are winds running sort of eastwards and westwards, if it's negative, it's west, and if it's positive, it's east. The models kind of agree with each other. There's some slight variation in the exact numbers, but the broad patterns are right. On the other hand, dust does not agree with each other at all. For the UM, we have a much stronger central plume of dust during the dust season, which isn't actually represented in the PCM. So one of the things we want to do is make our model more accurately agree with this PCM. And as I said before, this is average across 9 is longitude. You have then latitude, and then this is actually measured, the vertical profile is measured in something called scale height, which is basically the pressure at that level divided by the pressure of the surface. So it's going to be 1 at the surface, then up to 0 as you get higher up. So just to summarize what I'm actually doing and what needs to be done. Firstly, we're going to introduce the CO2 cycle, introduce some maps of formula inertia and albedo, introduce the formation of dust devils, because that's currently not in the UM. And we also got a small amount of water vapor in the atmosphere, which we need to add to the model. So I would like to finish by asking the question again, why Mars? So as I said, we're using the unified model, and this is therefore a collaboration with the Met Office. But as you may all know, the Met Office is only interested in what the climate is doing on the Earth. So why are they interested in a planet far away? Well, this here is a photo of a volcanic eruption in Iceland in 2011. And this eruption, it grounded all air traffic over the Atlantic and all over Europe for about 8 days and caused £1.1 billion in damage to the airline industry. So now Martian dust and volcanic ash have similar properties in how they disperse around an atmosphere. On Mars, there's less going on in the atmosphere, so our goal being, if you can get how that Martian dust spreads in the atmosphere, you can better predict how volcanic ash would spread in an atmosphere. So then hopefully we can then ground less flights in future. So what are some of the main takeaways today? So for manned explorations, a weather forecasting system would be really important. And there are many factors which go up to making this climate. And we hope, because that's going on in Mars, you can better understand what the effects of certain things are, unlike the Earth. For example, the Earth, you have lots of moisture in the atmosphere, but then you also have life. So Mars doesn't have that. So there's less sort of unknowns in the equation, if you like. Like I said, we can better predict the particulate matter of things like volcanic ash in our own atmosphere. And as Rafi had mentioned in the hard talk, the work going on in the X-Men group here with the unified model has actually improved how the Office use the unified model. To give you an example, we discussed earlier about tidally locked planets, which are planets which only half the planet receives solar radiation. And because of that, the way that radiation spreads in the planet is different to the Earth. So by getting really into the nitty-gritty of the physics, we can then say to the Office, okay, this is some of the changes you need to make to improve it. And come along to the Space Exe conference in 2024 to find out where to book for your next Martian getaway. So thank you. Is there any questions? That went a bit quickly.